Well, welcome everybody to Effective Acoustics, part of the B3 training program that is self-funded by the state to make sure that everybody that uses the B3 program understands the requirements and parts of it. My name is David Williams. Ostensibly, I'm a mechanical engineer. I would say in the area of acoustics. My dad was a music teacher, so I learned a lot about that. And I took a college course that was a prerequisite for Dr. Bose's class called Acoustics and Psychoacoustics of Music, where we got really intensely into some of the things that we're going to talk about today. And also we studied acoustics of the outdoor environment in my Design with Microclimate class. So that's me, and I'm with LHB and been there for 26 years now. And then I also have Becky with me.
Hi, I'm Becky Alexander, also with LHB. I'll come closer to the microphone. I'm an architect and researcher there, and I, on the other hand, have no formal training at all in acoustics. I don't think I even had anything in school. So this is showing you that if I can understand it, any of you can understand it too. And I've been at LHB for about 7 years and have been part of the B3 and SB 2030 management team throughout that whole time period. So just to provide some context, we're going to do a quick overview of what projects are required to do B3 and what it is. Most of you are familiar with this, but basically B3 guidelines are required to be met by all projects in the state of Minnesota that receive general obligation bond funding. All new construction as well as renovations that are 10,000 or more square feet and have the replacement of mechanical systems. The B3 guidelines are part of a larger suite of programs and tools that you see up here that are intended to holistically address sustainability from pre-design through design and construction and into operations. And B3 guidelines, you'll be setting project-specific performance requirements during design, designing and constructing to meet those requirements, and then during operations, confirming that those have been met. Now, the way that we do this for indoor environmental quality guidelines, like the acoustics guidelines, is actually through that purple one there, the post-occupancy evaluation. So that's a program that surveys occupants of B3 buildings at least 12 months after occupancy and asks them basically how satisfied they are with different aspects of their indoor environment. So we have the results of over 50 POEs from B3 projects that are informing kind of the continual revisions to the B3 guidelines. Speaking of those revisions, we've been undergoing a revision process that's looked holistically over the past several years. So starting in 2017, where there were new updates to the performance management and materials and waste sections of the guidelines, we're now looking at version 3.1, which includes updates to site and water as well as indoor environmental quality, including acoustics. And that is required for projects that started pre-design after January 1st of this year. So if you're starting a new project, it's going to be in version 3.1. Looking ahead, we have updates to the energy and atmosphere guidelines coming up in January of next year. And that will correspond to the rollout of the next version or the next step in SB 2030. That requires us to get to 80% better than an average building in terms of energy use from carbon-producing fuels. So we have some pretty specific learning objectives for this course that are related to specific definitions. But in general, the outline is we'll talk a little bit about how acoustics impact health and productivity, why we care, what are some design trends that are impacting acoustics. David will provide an overview of acoustics fundamentals and definitions and basics that will be needed in order to understand the B3 acoustics guidelines, which I will go through. We'll talk about what the requirements are and then kind of the process for meeting those requirements. And then David and I will each give a brief acoustic calculation demo at the end. So we do have quite a lot of content to cover, but we want to make sure that you're leaving here with all of your questions answered. So please feel free to interrupt with questions as we move through. And David or I will repeat them for the microphone because this is being recorded. But if we get into too deep of a rabbit hole, we might ask you to follow up with us one-on-one after the class just so we can get through all of the content. All right. Getting started, why this matters. So acoustics has been shown by the research to have a wide-ranging impact on productivity, health, and happiness. So we have external noises from transportation or industrial sources that can lead to things like sleep disturbance and high blood pressure. One study linked an increased risk of heart attack with nighttime road traffic for men and nighttime air traffic for women. So think about what you're hearing when you are sleeping. Internal noises from HVAC, appliances, or other people can hinder productivity. It can be distracting. It can make us lose our focus. It impacts memory retention and mental arithmetic. And then excess background noise from or inappropriate room acoustics can also hinder speech intelligibility, especially for those who have hearing impairment, language learners, or children who might still be developing their vocabularies and their ears. 1 in 6 words is not understood by the average first grader. So if you're thinking about missing that percentage of the content, that's a lot of learning that isn't communicated due to poor reverberation times in our classrooms. And then teachers raising their voice to overcome these conditions can lead to days of missed work, voice fatigue. On the other hand, so those are problems with not hearing clearly enough, we have people being able to hear others too clearly when they shouldn't be. So speech privacy is also a big concern and a big cause of dissatisfaction in buildings. It's really, really hard to ignore human speech when we're trying to focus on something else. With that in mind, here are some of the open-ended responses from the B3 post-occupancy evaluation surveys. So things like, I can't hear myself think, I hear everything, some of which I shouldn't hear my neighbors when they're whispering to each other. Corridor doors are too high off the floor, allowing sound to enter our room when we are trying to study. And very, very noisy place to work. Obviously, our needs were not too important. So these address too loud of background noise and then really that speech privacy between spaces, whether it's under a door, through the walls, or in other examples. So what are some of the design trends that are impacting acoustics? A lot of them are actually making our acoustic conditions worse. So we're moving more towards open floor plans, larger volumes of spaces with more hard surfaces, whether it's due to the love of exposed brick and concrete and exposed HVAC systems, less carpet in many of our spaces. So we have basically a lot more echoey rooms that we're working in especially, and a lot less speech privacy just because somebody might be having a phone conversation over here and somebody else is trying to work over there. What about energy efficiency design trends, David?
Well, I think some of the things you see is, well, for instance, in a room like this room has thermal displacement ventilation in. It's an extremely quiet HVAC system, which helps us in this kind of situation. But if this were in an open office, it would actually be too quiet. You'd too easily hear your neighbors, even though it's a very energy efficient system. We're seeing a lot more use of compressorized equipment, so that compressorized equipment sometimes is being pushed out into space. So in that case, you're the other way. It's more noisy than we have had in the past when you had a large central piece of HVAC equipment. And because we're doing more energy efficient equipment such as, and not necessarily energy efficient, but ecologically better, some of the refrigerants we use now are higher pressure refrigerants. That means our equipment has to work harder in order to do the duty to make us cool when we want to be cool in the summertime. And even things like boilers now, these fancy condensing boilers tend to have a lot more fans and widgets and things like that that can cause more noise in the background that we need to make sure that we're controlling.
All right. Yes, Rob.
Printed out 18.
Yes, I have one.
Do you have
I
one?
have one myself.
One of these?
Yeah.
Is that an extra?
Yeah.
Oh, thank you.
Okay, if somebody else
Did
comes
you say
in.
you also need one?
Hang on.
Were you asking for me?
We'll have this here.
I will say also some of the other kinds of things that impact our noise, which isn't necessarily related to energy, is, and we see in the school programs now, for special purposes, you have tunable lighting systems. And those tunable lighting systems require a dimmer that requires cooling, that sometimes gets put really close to where it would be convenient for the electrician to run the wires, which means it's right above the classroom where people are already maybe not able to hear what they should hear. So there are a lot of things that as our market changes, new technology comes in, we have to make sure we're getting them. So we're going to move on to talk a little bit about fundamentals of sound, trying to find that balance between nerdy enough And I'm not sure, am I entering? Am I spacing? I'm
Or you
spacing.
can arrow.
Thank you, sorry. Different computer. So, just going back to the basics, right? So what is sound? It's basically, it is energy, but it's energy that is being put into elastic materials, and elastic can be even a piece of steel in terms of sound, that's what we hear. And it's vibration that we can hear and sense. Because it is a vibration, we can use instrumentation to measure what the amplitude of the pulse of that sound wave and how fast it's coming. So we usually evaluate things both in terms of the loudness or the amount of pressure we have and how fast it's going or the tone that it's going. If we think about it, the loudness is how long that pressure wave is, how deep the pressure wave is, and the tonality is how long the pressure wave is. Now, you look at that and you think, well, that's great. You can see that even. You would be able to see that. But we're talking about things that are 4,000 times a second, for instance. You're not going to be able to see that. That's why we need instrumentation to see that kind of thing. Most of the time when we talk about pitch or the frequency, just in rough terms, this is 10 hertz on the left and 20,000 hertz on the right. That would be a really good stereo system if you could really do that. And most of our voices are in that 200 to about 4,000 range, which is why B3 for the most part focuses in that, 500 to 2,000 range, because that's the part that really speaks to speaking, as it were. And this other stuff, like especially lower than 200, tends to be things like artificial machine noise more than anything else. When we saw that first slide a couple slides ago, we had the nice sinusoidal wave, which is perfectly made and cannot really be created in nature. So this is just to say this represents middle C produced by 3 different kinds of instruments. And you can see the waveform looks different, but the frequency is the same. So back in the days of analog synthesizers, you would take the first one and you could break it up into the second one, and then you could put another filter on and cause it to be the third one. And that's kind of the fun part of that age, which is long gone now. We will sometimes see information presented to us when we're looking at mechanical equipment or any other kind of equipment that talks about sound power. And the sound power is what is being, or also if you're buying a set of speakers, it's going to say SPL, which is the sound pressure level that speaker can produce given 1 watt of energy coming in. That's the raw power that the device can create. But normally when we're talking about the built environment, we're talking about sound pressure, which is the change in air pressure of the sound wave as it's getting to us. Somebody said, well, let's take this sound pressure that's coming to us and we're going to create a great thing called a log number that will just say the scale is 0 to 100. It actually goes beyond that, but I mean, we'll put it together and you have this powered number, which when it's logarithmic like that, it's doubled every time you add 10 to it. So the math is down below if you want to add a bunch of decibels together, but I don't think many of us own calculators that can do that right now, at least on their desk. Comparative sound levels in dBA, and we'll get back to what dBA means, go from about 110 down to around 10 is the quietest you can hear. And you can look in your handout about what kinds of noises we hear. Generally, OSHA is going to say if you have a space that's more than 85, you should be wearing hearing protection. So don't be using your blender for too long, or else you're going to need to wear.
Could you talk about how if I have a vacuum cleaner at 70 and a garbage disposal or shouting at 80, how you can add those together?
Adding sounds together, well, okay. Thank you for that. The interesting things, because these are log scale, and as we mentioned before, you can't add them directly. If you took two sounds that were 60 dB, had them both in the same room at the same time, it's not going to be 120 dB. It's going to be basically 63 dB or something close to that. If you had a sound that was 60 dB and one that was 70 dB and added them together, it's going to be basically 70 dB. Because that 70 dB is twice as loud as the 60, you just barely are going to see the difference between them. So anytime you have a large difference between two sound numbers, you're going to be pretty close to what that upper number is. When they're both about the same, you're going to have a slight increase in terms of the total amount of dB. And normally in the case of a B3 project or anything we're doing, we don't normally have to add dB. If you have to do that, you're going to do the same sort of math in that previous thing that I showed where you're adding the dB with the logs and everything else. So you could go crazy doing that. It's easy to find an online calculator though if you really wanted to do it. If we want to look at what some various noises are, and we're going, in some ways we're jumping back and forth a little bit, but if we go back to what we were talking about before, which is the loudness and the frequency is like the tone, what it sounds like to you compared to, say, a piano. Various kinds of equipment or ambient noises have different amounts of loudness at different kinds of frequencies because everything is kind of blended together. So a pile driver, you can see on this particular graph, has a lot of impact at the low frequencies and teeters off as we go to the right. And then the ambient noise has got kind of a gentle curve off to the right. Some of these other things are specific noises created for the purposes of a sound testing program so they can check your visual or oral acuity. So I feel like I haven't spent quite enough time on that, but I guess, again, this is all background, right? So we have a pressure wave. It's got frequency to it. It's got multiple parts to it. And it's being produced by equipment out there or people out there or dogs barking, whatever it happens to be, and it gets to our ear. Now, our ear is kind of a funny shaped thing. It was meant to kind of bring sounds into our ear. It's meant to help us locate things. Well, the ear design means that it doesn't necessarily bring all that force into our ears quite the way that we expect to. Now, some people that are doing very accurate and careful kind of sound analysis, they have these foam heads with ears on them so that they can really check. You know, if you're doing a concert hall or something, you might have the fake head to do that. But the main thing to remember is it's nonlinear in response. Your ear doesn't hear things at the same level a piece of a microphone will. So we have to compensate for that. The other thing is your brain takes that sound that it hears from the ear, takes the electrical waves that it hears, and it does something else with it. It does other kinds of things so that you think that you hear something. We all know we don't hear the same thing. One of the things that I learned in my psychoacoustics class is if you take the overtones of a tone and just play those to someone, your ear and brain combination will think that it's hearing the bottom note. That's the magic of the Bose speaker. It can't possibly create the tones that you think you're hearing, but it fakes your ear to do it. They just made sure that they're taking care of all the overtones. So if you hear the overtones, you think you're hearing the real note. And you're not hearing the real note. It doesn't happen. It's just all made up in your head. For all these reasons, well, they've had to come up with what's called an equal response curve so that any person hearing a tone, whether it be a low frequency or high frequency, can think it's the same loudness. This is kind of the agreed on ear and brain response where somebody putting up their hand will say a 100 hertz tone sounds the same as 10,000 hertz tone at a given sound pressure level. A couple interesting things to note is if you notice the sensitivity of your ear to sound is greater or I should say it falls off more at low levels than at high levels. So we're gonna see that when we look at some of the weighting factors, that if it's a quiet sound, more of a bass note is gonna be a little harder to hear than when it's a louder sound. So what does that mean? What that means is somebody has made an ANSI standard, of course, that says if you hear a tone and you're trying to measure it for human response reasons, that you have to create a curve so that we can come up with a reading that means something so we can compare things. So we talk about dBA, you've probably seen that a lot. You've seen dBc probably, both A and B are used in the B3 documentation, and B we hardly use. And then there's just plain dB. So plain dB is the straight line, 0. And then if you look below that straight line, those are the various amounts of filtering that is done to equalize sound pressure to fake our ear out. Now, the big difference between A and B is that A is really for kind of normal type environments like we're in right now. And then as you go into a louder type environment, you start using the B scale and the C scale because it compensates for the fact that your ear is different for louder sounds, which we'll see later when we're talking about STC and OITC, and also the S1260 ANSI document that talks about sound in our interior spaces, that we want to look at both A and B because we're concerned about noises that are generated inside a space, and we're concerned about noises that are generated outside the space and can come inside. So C is often used for outside type noises because it's got more of an emphasis on deeper sounds like cars, buses, automobiles, whereas A is more like we're having conversations right now about. So very complicated. Again, this is just basic so you can say, yeah, okay, there's some math involved here. If we're going to use a sound meter, octave band type sound meter, we're talking about octaves. And, was I supposed to talk about octaves already?
Yeah,
yes?
what's an octave?
Okay, thank you. Thank you for that question. So octave is a doubling of the frequency. It is also on a piano, if you hit A above middle C, it's 440 hertz. The next A above that is 880 hertz and continues on. So when we talk about octave bands, which is just an artificial way to divide it so that we can look at it without having a gazillion pieces of data, it's just taking that basic number of hertz and then doubling it every time. So we kind of look at sound data a lot of times in octave bands. You can look at it in third octave bands. You can look at it in 12th octave bands. You're just trying to aggregate the amount of sound energy within a various kinds of tonal energy. Here's an example of a very loud thing that's going on. It's probably equivalent to a jet taking off 2 miles away. And you can see that we have the original level is the third line down. And then there's an A-weighted correction. And you can see that the correction mainly occurs at the low end. And we come up with a resultant dB. You can see it's only 31 dB in the 31 hertz range, which you would really more feel than hear. And in the key area where we're trying to speak, you're in that 85 to 95 range. It's pretty loud. But when you do the math on it and come up with a pure dBA number, it's 103 dB. So that's a very loud space in this case. So that was very quick into dBA, dBc, and dBs and octave bands. Now the other kind of thing that you have to worry about when we're talking about B3 is NC. So you say, well, we have all these other things, why can't we use those? What is NC? So NC is another way of looking at it where we've taken, again, a sort of evaluation of what somebody would say is reasonable in a space. And in this case, we've plotted a sound that you're measuring using an octave band meter, and you look at every frequency, and basically the NC curve that it is below is the NC you have. So in this case, this is an NC 45 space. based on those frequencies. Now, what does that tell us? It tells us that if we want to improve this space by a substantial amount, say get down to NC 35, we could dampen all the frequencies from 1,000 hertz up, and we would achieve that. We don't really have to worry about any of the low frequency stuff at all. We just have to worry about the high frequency stuff. So that's usually good for mechanical engineers because some of our stuff tends to be loud and thumpy. And we can just get rid of the hissy stuff, which is a lot of times electronics anyway. So we can blame the electrical engineers for that. So this is the common way. Now there's a variant of this that I'll just touch on for a second, which is, that's called RC, or room criteria. That's supposed to help us characterize in the HVAC world whether it's a hissy kind of sound or a rumbly kind of sound, or it's likely to be irritating. But that's not part of B3, and it's really just one of those things that when you go to the ASHRAE handbook, it's on page whatever, and it tells you how to do it, and even if you calculated it, you wouldn't know what to do with it, who to give it to, or what they would do with it anyway. So those are kind of the common rating systems that we would have. Now, to make this a little easier to swallow, we will repeat for the people that saw this at Impact, this particular thing, which I need to click here. Nope. Click there.
Everyone to the 9th Annual Symposium on Artificial Intelligence. Now everyone get ready. We're going to spend several intense days together listening to speakers, attending workshops, etc. But we'll also have some fun and we'll have some downtime in between. Now if you look in your folder on the yellow sheet, you'll see that on day 1, we will concentrate on the development of computer capabilities for intelligent behavior in complex situations.
So what they're trying to do with this video is demonstrate how well you can hear someone depending on how noisy the room is. So a room meeting NCs from 30 to 50 to show that. So we have a similar, oh, that's the same one. It's playing automatically. Okay, cool. All right. So that's NC, which is the way we talk about sound in a room. This room obviously has a very low NC in here. We also talk about room acoustics in terms of reverberation time. Now this room also is very dead. It doesn't have a lot of reverb time. Basically the way that can be calculated is, or measured, is they do an artificial sound like this and you see how fast it decays. So how quickly does that go? A space that you might want to have really reverberant would be maybe a worship space or an auditorium where you can kind of smooth things out. But if you want to have a speaker speak, you want it to be very short. There's so many reasons why the multi-purpose type spaces that want to be, conference spaces and theaters and music performance spaces fail is because they should have different reverberation times and they don't. We talk about the sound absorption coefficient and the noise reduction coefficient of materials. So what we're trying to do with those is decrease the reverberation time, because if we can take that sound energy that's in a space and get rid of it every time it touches a surface, then we're going to reduce the reverberation time. So that's why you see, for instance, in this room, soft surfaces there, a semi-soft surface on the ceiling, certainly better than the concrete. That's all trying to absorb sound energy and reduce the reverberation time. Now, the other thing that's fighting you when you're doing reverb time is as your room gets bigger, it takes longer for a sound to go from one side to the other side and come back. So naturally, a bigger space is going to have more reverb time, so you have to do some things to control it. Of course, you have the other advantage that sound decays across distance too. So
I just also would point out on that last slide, David, that the sound absorption coefficients vary by frequency, so you can see those different octave bands in the table below. So a certain material might be like gypsum board that's 1/2 inch thick might be more absorptive at 125 hertz than it is at the higher frequencies. And then one number that tries to average out the sound absorption coefficients is the noise reduction coefficient, so that last column. And that just looks at 500, 1000, and 2000 hertz as those frequencies that are most important for speech intelligibility. So those will come into play when we talk about reverberation time and noise reduction coefficients as part of the B3 guidelines.
And I think, again, looking at the sound absorption coefficient, you know, things like, say, air noise or high-pitched noise, you can very easily get rid of through use of, things like these soft boards behind us. That's easy to do. It's much harder to get rid of low-pitched noises because there are not too many materials that can absorb that energy from that low frequency. If we're going to look at some other materials and how much they absorb, here you can see how the fiberglass board is really great at those high frequencies and really poor at comparatively poor at the lower frequencies. And there's some various other materials, again, wood being kind of in the middle. We want to really, so this is all about how to absorb sound. We have a similar type video here looking at reverberation time. When we play this one, you know, basically it will look at reverb time starting from 0, perfectly dead room, and up to a 4-second reverb time. So that's...
Welcome everyone to the 9th Annual Symposium on Artificial Intelligence. Now everyone get ready. We're going to spend several intense days together listening to speakers, attending workshops, etc. But we'll also have some fun and we'll have some downtime in between. Now if you look in your folder on the yellow sheet, you'll see that on day 1, we will concentrate on the development of computer capabilities for intelligent behavior in complex situations and program synthesis, followed by an afternoon of miniature golf and a fajita dinner. Now on day 2, we'll have hands-on workshops dealing with multi-source information integration and autonomous robots, followed by a crawfish boil and karaoke. Hey Stevens, are you prepared to give us a repeat of last year's performance, huh? And on day 3, we'll all take a field trip to the AI Center, focusing on natural language processing, engineering tools, and distributed systems. In the evening, you can play volleyball, visit the hotel spa, or take the rest of the night off if you like. On day 4 will be a leisurely one. There'll be a pancake breakfast to start off with. There'll be a word ceremony at lunch, and after that, you're all free to go home.
So there we have reverberation time. So that's how you control sound, or those are the things that are important for controlling sound within your room. So if your room is too lively, you need to absorb sound, those are kind of some of the things that you need to look at. The other part that's in B3 is acoustic separation. In other words, separation of sound from space to space, from the outside to the inside. Basically, STC and the inside really focuses on dBA and looks at frequencies from 125 to 4,000 hertz. And going to the outside, again, it's using that DBC curve, so a little more emphasis on the lower frequency, but usually the threshold is set higher. And you're looking at lower frequency category in the procedure. And it's a kind of complicated procedure that's related to, again, using kind of a graph and then figuring out what your 500 hertz number is, and that gives you the number. But they're very related to dBA and DBC. And then impact isolation class really is primarily a housing type thing where, this is why we see a lot of times now gypcrete and various kinds of barriers to impact so it's not going through the floor. Let's see, if you really wanted to know, I have all kinds of really nerdy language there. And so here is an example of a sound transmission class, a demonstration between, this happens all the time, a discotheque and a conference. I did this wrong again. Okay. Hello. Oh, no, too far.
Welcome everyone to the
Thank you.
9th Annual Symposium on Artificial Intelligence. Now everyone get ready. We're going to spend several intense days together listening to speakers, attending workshops, etc. But we'll also have some fun and we'll have some downtime in between. Now, if you look in your folder on the yellow sheet, you'll see that on day 1, we will concentrate on the development of computer capabilities
Angie Johnson earns the smiley face
for intelligent behavior in complex situations and program synthesis, followed by an afternoon of miniature golf and a fajita dinner. Now on day 2, we'll have hands-on workshops dealing with multi-source information integration and autonomous robots. Followed by a crawfish boil and karaoke.
So if you're paying attention to the partition insertion loss, you can see again the kind of characteristic curve where we're doing more attenuation at the higher frequencies than the lower frequencies. And then this one is the combining the NC, the STC, and reverb into one kind of video.
Okay, class. First, I'd like to congratulate each and every one of you for making it this far and listening to us. And you have just one approach left. It's a big one. Final exam consists of 3 parts. Account for 40% of your grade. That's 40%. But if you listen to what I tell you today, do what I say, you will pass. Part 1 of your quiz. Start with the Byzantine Empire with chronological historical details, including the Crusader conflicts through the Middle Ages up until the time when the Ottomans took Constantinople. Part 2, provide parallel timelines for development of the Mayan Empire and their move to the Yucatan, the Incas' establishment of Cusco in Peru, and the Aztecs' establishment of Tenochtitlan. Finally, for Part 3, be prepared to follow the Chinese Southern and Northern Sung time periods through the Ming dynasties, not excluding the Great Mongol War.
All right, so very quickly, probably too fast, we kind of covered the major parts of sound that we care about in B3. And now we're going to talk about how B3 is interesting. So do we have any questions on this part of what we've done so far? You guys are just stunned, aren't you? Too much sound.
I've got a question.
Problem.
The noise, the NC, noise class or noise?
Criteria.
Criteria.
Is that a property of the space itself, or is it just kind of, this is a measurement of what the sound is doing in the room?
It is a measurement of of what's happening in the room related to all the sound that is created in the room. So the majority usually of the sound that's coming in the room is HVAC. So a lot of times that's the calculation that's done is, let's start here with the large piece of equipment making noise, and how is it attenuated, or from any other space outside. And then you look at what noise is generated in the space and what comes around the partitions, how well is it sealed, what kind of materials separate the space from the noise sources. So
It's kind of a combination of how much noise is being broadcast into the room and also what's being done
then-
by the room.
correct, yeah. Yes,
So if I'm designing a room to be NC25, does that just mean that I can design each component that's affecting the room to NC25 and then the room as a whole will be NC25?
not necessarily, because for one thing, you could have somebody else producing noise, which is part of it. And the other thing is you have to account for everything that's along that path. So, if you have a piece of equipment that's producing, say, 85 dB at the far end in a number of different octave bands, depending on the size of duct, how many fittings, how far away it is, all that's being transmitted down the line to get to us. If we have a VAV box above the room, that's going to create noise itself right there. And you're rarely going to find a VAV box that's going to be NC 20, box. The other thing is, say that VAV box is in that room, you think you've selected 25, but that room doesn't have a ceiling in it. Well, the ratings for all those VAV boxes say it's assumed to be above a ceiling. So now you got to do the math to figure out, well, what happens if it's not above a ceiling? You got to do some other things like that. So while that's a good start, there's a lot of other sources that are going to come into your space that can create things.
And David will be doing a short demo on NC calculations, just showing kind of what is
What
included.
goes into it, yeah. Okay, anything else?
All right, on to the guidelines. So in general, with the B3 guidelines revisions process, we're hoping to harmonize the guidelines with practice, which is why the B3 management team invited hopefully many or all of you to focus groups to talk about indoor environmental quality, sent out the drafts for comments and that type of thing. So thank you for participating, for those who did participate in that process. For acoustics specifically, we had several lessons learned from previous versions that we tried to address in this newer version. One, feedback from those post-occupancy evaluations that acoustics is a leading cause of dissatisfaction. So that came out somewhat in the numbers, but really it's one of the things that gets highlighted in those open-ended comments as well. When people are unhappy acoustically, they're really unhappy. So to address that, the approach for the B3 guidelines is to address each acoustic phenomenon separately, and this is in alignment with national standards and green rating systems where it's appropriate, so making sure we're addressing noise from the space next door, speech intelligibility within the room, outside noise, all the things that David has talked about. The other lesson learned is that the acoustics calculations are a little bit difficult, it seems like, for us professionally to really wrap our arms around and to perform, especially if we haven't done it in the past, and especially if we don't have a relationship with an acoustician or acoustic consultant that we would typically go to for this type of request. So we've seen this in the B3 guidelines where the acoustics leader, which is a role within the B3 guidelines tracking tool, is often left blank. And that kind of makes sense because somebody who might be able to do the calculations that David's talking about for noise criteria wouldn't be the same person who's doing a reverberation time calculation unless it is that acoustic consultant. So we'll talk a little bit about that. So to address this, we're trying, where feasible, to provide multiple compliance pathways, so it might be a little bit easier to do the calculations. But for the most part, it's just about providing training, making sure people are aware of what these things mean, who should be able to do them, and when they need to hire an acoustician or consultant when they're not comfortable doing the calculations on their own, or for more complicated spaces or scenarios. So the intent behind the acoustics guidelines are to promote productive, supportive, and comfortable acoustic environments for all occupants and to control unwanted noise. And effective acoustics enable effective speech communications at normal speaking voice while also providing for local speech privacy. So the four main areas that we're looking at here are blocking outside noise, minimizing background noise from mechanical systems, limiting the sound transfer between spaces, and then within a room or a space, ensuring speech intelligibility and acoustic comfort. So like some of the other indoor environmental quality guidelines, we care about these most in the spaces where people are really affected by them. So if it's a bathroom or a corridor that is just being used not for very long at a time, we're not requiring really strict acoustic conditions. But for spaces that are occupied regularly, which B3 defines as occupied by one or more persons for more than 1 hour, during days the building is in use, that's where these are required. And this is where we feel it's most important for occupant satisfaction. So some examples, this will vary depending on the program of the space, but offices would typically be regularly occupied, conference rooms that are booked out for more than an hour at a time. If your lobby has somebody who's stationed there for more than 1 hour at a time, whereas not regularly occupied corridors, coffee areas, break rooms where people aren't spending too much time in there, for example. But you would go through the exercise with your own program of saying, okay, which spaces are likely to be used by one person or more for more than 1 hour. So the B3 guidelines, this is the approach to each of the four areas that I mentioned on the earlier slide. So blocking outside noise, we have two pathways, and we'll go through each one of these in more detail. So this is just the summary overview, big picture. The two pathways are to measure the dBA in each of those regularly occupied spaces after construction to see the amount of exterior noise that's coming in. So there's a maximum threshold for that. Or having your exterior envelope, your walls and your roofs, meet an outdoor-indoor transmission class rating. So that's the one that David mentioned is more based on DBC rather than DBA to block that exterior noise. To minimize mechanical noise, we're looking at that noise criteria rating. To limit sound transfer between spaces, we're looking at the STC or sound transmission class rating for interior walls and floor ceiling assemblies. For sleeping areas and dwelling units, we're also looking at reducing that structure-borne noise, the footsteps, from the impact isolation class rating and the floor ceiling above the space. And then these are all need to be supported by construction details that B3 also addresses a couple of. For ensuring speech intelligibility and acoustic comfort, there are two pathways here: reverberation time, which David mentioned, or average noise reduction coefficient of all of the interior surfaces within the room. So we'll talk about that a little bit more. Okay, before you think, well, this is pretty clear and you really have your arms around it, there is actually kind of a separate set of requirements for learning spaces. And this is because in the state of Minnesota, K-12 classrooms, K-12 learning spaces are required to comply with the ANSI S1260 2010 standard, which is specifically written for schools. And so in order to align with that, and because this standard does include thresholds that are really appropriate for spaces where verbal communication is really critical to learning, B3 has also adopted ANSI S1260 for spaces that you would designate as learning spaces. So definitions, it has different thresholds for core learning spaces versus ancillary. Core, good speech communication is really critical to the program of the space, whereas ancillary, it might be more informal learning that's happening. So examples of ancillary would even include cafeterias and gyms. And then not included would be spaces that might have specialized acoustic needs, like swimming pools, auditorium, music performance spaces. So this is not just K-12 anymore, this is required for spaces that qualify as learning spaces within any of your projects, B3 projects. So we are still addressing the same basic acoustic areas, but we're doing so a little bit differently in ANSI S1260, and the thresholds are a little bit different. So a couple places where the metrics are slightly different, blocking outside noise, we have, instead of the maximum dBA or OITC option, we have maximum dBA and maximum dBc and minimum OITC rating. So it's kind of more, and then the thresholds are different from B3 for other spaces as well. For minimizing mechanical noise, instead of noise criteria, we are going to dBA and dBc. So again, that's addressing both of those. Limiting sound transfer is similar in terms of the approach to STC. The impact isolation class is required whenever, for any space that has, any learning space that has another program space above it. And then reverberation time is the pathway for ensuring speech intelligibility and acoustic comfort. And you'll see in your handouts that the slide deck includes the specific requirements for the ANSI standard in addition to the B3 requirements for other spaces that I'll be going through. I've hidden those slides in the presentation just so that we can get through this in a little bit less confusing and more condensed way, but they're there for your reference, and I have this copy up here if you have specific questions about learning space standards. So going through one by one, we're back to the non-learning space. We have the two options of measuring the dBA from exterior background noise, and the threshold there is 45 dBA. This happens post-construction, but pre-occupancy in regularly occupied spaces where you'd have the mechanical systems turned off, you're making sure you're just getting the noise coming in from the outside. Or we have the pathway of those outdoor-indoor transmission class ratings. And for that, there are two thresholds. One would be for a typical site, and another would be for a site with an identified noise risk. B3 guidelines defines exactly what that means. It's calculated based on a 24 hour average number that's produced. And so basically your first step, if you're going with this pathway, would be to decide if you have a high risk noise site. You look at an airport map if you're near an airport to see if you're automatically within that threshold. And then if you're not, then you would go to an on-site 24-hour measurement. And from that, you'd be able to calculate whether you're a high-risk noise site or not, or your acoustic consultant, whoever's doing that measurement for you would. If you think that you're probably in a high-risk noise area, you're right in an urban area, a lot of traffic, you can feel free to just assume you're in a high risk and go ahead and design for the higher OITC.
And we believe that most B3 buildings or buildings that have to comply with B3 would generally be of heavy enough construction that you're not going to have any problem with the OITC anyway, because it's all pretty long-lived, high mass type buildings. I think the only time you maybe would be into a situation would be a lot of glass. Then you probably would have to look carefully at what kind of glass system you're using, whether you can hit that OITC number of 40 if you're in a high-risk area.
And just so you know, the definition of high risk is 65 dBA for kind of an average over time. And so to compare, we had an acoustic measurement done outside our office in the North Loop where the Free House is. And it's right on Washington Avenue in the North Loop of Minneapolis. And that was 69.8 dBA for that kind of rush hour time frame.
Was it less if you would do it over 24 hours? Is that like the peak?
That was the peak. Yeah, we didn't do it over 24 hours, just the peak. Okay. The next is minimizing mechanical noise through the noise criteria. And so you can see there are different thresholds for different types of spaces, with the strictest being for those meeting rooms, lecture halls, offices smaller than 300 square feet, and conference rooms where speech communication without loud background noise is the most important. And David, again, will be showing a little bit more about what impacts this, but the equipment and the distribution system of the air is really critical in this one. And you can see the requirement is NC levels from air distributed mechanical noise. So it's actually not taking into account some of those other non-mechanical noise sources that David was mentioning earlier. Limiting sound transfer between spaces. We have a requirement for minimum STCs if you have two different occupancy groups. So if you had that lecture hall next to the disco, that would be an example of two different occupancy groups where you need a really strong high STC in between them. And then we have a lower threshold for walls and floor ceilings within occupancy groups. So between one office and another, one classroom and another. And those vary based on, for assembly it will be higher, for business it might be a little bit lower. And then those are also supported by construction details, so making sure that you're not thwarting your STC with poor construction details. So just as some examples of how you can increase your STC, and I bet many of the architects in the room are most familiar with STC more than probably any of the other metrics we're talking about, but basically increasing mass, increasing airspace, wider spacing between studs, staggering studs, and using resilient attachments. And what's not shown on here, but could be actually a larger potential STC increase than any of these, is including that sound insulation in the cavity as well. So there are lots of gypsum, pretty much every gypsum manufacturer, every large manufacturer will have a catalog with their own assemblies that they did the tests on to show what STCs you can achieve with different types of their product. But this is a version from HUD that is just showing for wood studs what the impact of adding attenuation blanket, staggering studs, in having a double row of studs with an airspace in between, adding a layer of gypsum board. So that ranges from 35 at the top, which wouldn't meet any of our rated wall requirements. 40, I believe it might be actually 45. Let's just double check. 45 is the lowest requirement and 60 is the highest. So that 46 one would meet the lowest level, 51 would meet 50 level, there's a 55 requirement, and a 60 requirement. So this is kind of just showing the range. And as you can see, there are implications here, both in terms of the amount of space that the wall is taking up and in terms of the amount of materials that the owner is buying for the project. So this is important to know during pre-design, kind of how many STC rated walls and at what level you'll be including in the project, and making sure you're getting, if you are solving the problem with increased thickness, making sure that's in the plan before it drives your whole drafting team crazy redoing everything. But it doesn't have to be done with thickness. I think especially with some of those resilient solutions, it can be done in many different ways.
Is SDC within certain frequencies, or is it? So when
Yeah.
I see a 63, is that from 62.5 up to 8,000, or is it?
Well, they basically create there's a series of curves that's in ANSI. And what they do is they'll plot the sound, they'll have a test sound over here, they'll measure it on this side, and then they'll figure out at what value 500 hertz is. And they'll compare that. But the attenuation is roughly like the amount you would attenuate off a DVA type sound.
So it's weighted.
Roughly.
It's
a
weighted similarly to
weighted
DBA.
Scale, and if you want to look at the ANSI thing, it's there. But it's again one of those things that's supposed to be done in the lab. So every one of these assemblies that they'll publish have been done in a lab. They have a test cell, sound on one side, receiver on the other.
That's a good point. Is B3 distinguished somewhere between lab and field values for like STC?
I think there is actually, for STC specifically, a accommodation for, I'm trying to, I guess the only thing in here is STC versus apparent sound transmission class ratings, in which case you can subtract 5. I don't know what apparent sound transmission class ratings are.
I don't know, I would, it gets weird anyway, because you have some, like in a gypsum handbook, we were just doing this on a job where we wanted 54 room to room, but that design required the electrical boxes to not be back to back, which the contractor managed to do. So, but luckily, these were also supposed to be fire rated, and they had to put fire rated putty around the back of the boxes. That rating was 51. Oh no, that was 54. It was above the 51 we were supposed to be. So, by luck, we had specified ourselves into a solution that worked, even though, appropriately, it didn't follow the standard exactly.
It looks to me, though, that these are all tested and design numbers, not measured numbers, with the exception of that if you go the measured pathway for outdoor.
There is a way to do a
noise
field
intrusion.
test, but it's not pretty either. And it's not quote official, right?
Yeah. Okay. All right, so then supporting this great wall that you have with construction details is really critical. So B3 does require extending the wall to the structural deck above and then limiting the penetration. So that middle one is the example of the back-to-back electrical boxes that the sound's going to travel right through. Top one, you can see air, the sound's going to be
Go
able
out
to
here in the
get through.
hallway, and where the people work there, I think the walls only go so far because they've got ductwork or pipes going through
Oh,
the
sure.
glass wall, and that glass wall, I don't think has a hole perfect for that.
We were practicing for this presentation in a room that had that top condition and had, the bottom condition actually is a door that has a 1-inch kind of gap all around it. It's a rolly door, but even non-rolly doors also can fail to be acoustically sealed. So we were in a room that acoustics was traveling straight through, sound was traveling straight through the wall in many different places. And we were hearing the conversations of people in the open office next to us, and hopefully they learned a lot about acoustics. Okay, so that was for all regularly occupied spaces. This is just for mechanical rooms, so recognizing that mechanical rooms are often loud sources of noise, so there are minimum STC requirements for that, as well as construction details, in addition to those limiting penetrations and the walls continuing to the structural deck, isolating the mechanical equipment to limit structure-borne sound and vibration, and then as plumbing equipment as well. This is the only requirement that's specific to sleeping areas and dwelling units that impact isolation class of 50 for floor ceiling assemblies, and again, this will also be required above learning spaces. For speech intelligibility, we have two different pathways. One is the reverb time, and that's looking at those 3 different octave bands. Each one needs to meet the threshold. It's a range from 0.2 to 0.7 seconds. For most space types, it is a little bit more flexible or lenient for open offices, recognizing that bigger spaces will have a longer reverberation time. And then the other option is looking at the average area-weighted noise reduction coefficient of all interior surfaces. So looking at all of the surfaces that I can see in this room, saying, okay, the noise reduction coefficient of concrete is 0.0 something versus of this acoustic material might be a 0.8, 0.9 something, averaging that out based on the surface area that they take up. And at the end of the day, they need to be at least 0.45 for most spaces, 0.35 for spaces within smaller volumes, and 0.30 for open offices. So the reason why there are 2 pathways to compliance here isn't necessarily that it's a lot easier to calculate NRC than it is for an architect, say, or an interior designer to calculate reverberation time, but rather it's more flexible. So if you do have an open office or you do have a really large space, it won't meet the reverberation time requirement. It likely will not meet that just because of the volume of the space. You're still able to include that space in your B3 project, but it will need to include more sound absorptive materials than you might otherwise have. So typically, smaller spaces will have an easier time meeting the reverberation time requirement, and you might not have to have any sound absorbing materials in them, whereas these 2 pathways are intended to be pretty similar for most typical size spaces with typical applications of materials. And then when you get to the very large volumes, it will be easier to meet the noise reduction coefficient pathway than the reverb time pathway. And my demo will be on calculating the reverberation time. So we'll talk more about that in a little bit. Okay, so those are all the ones that we've talked about already. There are 2 additional guidelines that are a little bit more specific. So this guideline is an additional way of ensuring speech intelligibility in spaces that really need it, and it's based off of a Minnesota statute, so that's why this language is really specific. It's required for spaces intended for gatherings of 15 or more people where audible communications is integral to the use of the space. So if you have a permanent audio amplification system in the space, you'll need to include audio induction loops for hearing aids and cochlear implants. So that's one part of the requirement. The other part is meeting the maximum background noise and the reverberation time thresholds set in the same ANSI standard that the state of Minnesota requires for K-12 schools. So that's pretty much already covered by other guidelines. So this is just for gathering spaces for 15 or more people. And then finally, for projects that are not compliant with some of the other guidelines, and this isn't that, okay, well, this is an alternative path to compliance. This is, say, you have a renovation where you're not touching the exterior wall or you're not touching the interior walls, or you haven't changed the volume of a space so you can't impact the reverberation time very much. Then having a sound masking system implemented that meets these requirements is what this guideline requires, in addition to, so for spaces that either aren't compliant or that might need additional sound privacy. So say you do have an open office, it meets the NRC pathway of the reverberation time / NRC requirement, but you still think there's not going to be enough speech privacy and that will cause distractions within the space. these are some guidelines you can follow for implementing a sound masking system. Okay, are there any questions about the B3 guidelines requirements before we go into kind of the process that we would use to meet those? Yes.
So if someone complains, someone is to measure the sound levels in the space after the fact, like that. So I do commissioning for the U.
Okay.
And every time we have a noise issue at the end of construction,
Yeah.
I say, hey, my space is too noisy. And I mean, it's very obvious. I mean, you walk into space, like, okay, you can hear it right away. And then we measure the noise criteria and compare it against the noise criteria curve, and then you say, yeah, it's too loud. So then is that part of the B3 process now? Or
Well, so
they ask for?
remind me, so commissioning is part of the B3 process. I don't know that acoustics commissioning specifically is part of it, but I hope that would be addressed in the mechanical systems commissioning.
If it's too noisy in the space, and it's supposed to be a B3 project, then it has not met the requirements of this. So somebody would be supposed to be doing corrective action. You know, I only say supposed because we've all seen those projects where the corrective actions don't occur, for
I mean, it's not
instance.
an easy task sometimes, right?
Yeah,
It's expensive
no.
to fix, sometimes.
Sometimes.
Yeah,
So-
I think a follow-up for us would be to check out the commissioning requirements and to see if they do
Just testing,
include.
right, I guess.
Yeah, to
Either
the-
the acoustician or the engineer, or
Yep,
in this case it's us because we have the tool.
Right.
I mean, outside.
Right.
Yep.
so you can get them on, you can do octoband analysis on your phone now, so it's kinda crazy.
Yes.
So there may be projects where it'd just be easier to spec the sound masking system and skip all the costs and labor and time.
Yeah,
doing the
that's-
calculations.
Right, that's
wouldn't
why.
we go right to the-
That's why I say it's not an alternative compliance pathway. It's when some of the other parts of the guidelines aren't applicable and you would have request a variance for them because it's not included in your scope of work. So not that acoustics calculations aren't included in my scope of work, but exterior envelope isn't included in my scope of work. Or interior finishes aren't
Yeah,
included
if
in
you
my
already
scope
have a
of work.
box and you're just changing the occupancy, for instance.
I was wondering that same thing when I saw spaces that aren't compliant though, so I asked. Yes.
So, sound masking adds some decibels to a room too. We have a really
Yes.
large room, coffered ceilings through 2/3 of it, and a even higher ceiling on a third. A lot of hard wall surfaces, it's supposed to be a library, and so the complaint is that people can hear what's going on all over the room. But if we add sound masking, then I hear from other staff that just hate the idea of the white noise. So where's the balance? Is that a workable solution, or is there a point where just normal speech is just gonna be too loud to mask at certain distances?
Yeah, I mean, sometimes there are gonna be inherent problems that can't be solved unless you start dropping in, you know, sound panels or something like that, right? You know, for the most part, this is newer projects, so hopefully people have designed it in to begin.
Yeah,
And then retrofit becomes a little more complicated and,
yeah, well,
you
there's
know,
situations
you
that,
take
existing
you
building.
DXS a stack of shelves and put in some panel instead, which
Yeah.
probably wouldn't go over well.
Oh, yeah, because for the library, nothing is allowed to be checked out.
Oh.
So security and sightlines are a huge issue as well.
Yeah.
So we can't just chop it up into smaller spaces.
So I think one of the things there is having the max, like the 45 dBA max, so it's not, you aren't just continuing to up and up and up the background noise. But, yeah, if you want to talk more with David afterwards.
Do you like it in our office,
Okay.
by the way? Because we have it in
We're
Minneapolis.
not gonna talk
Okay.
about that right now. We're moving on. It was right over Maureen's desk. Okay, so how do we actually meet these in practice? So we'll talk about what team members are looking at, which guidelines typically, what you should be thinking about during different stages of the design process. And hopefully we'll need to go quickly through these so we can get to our demos as well. So I'm going to skip I6A, which is that for learning spaces, ANSI standard, as well as I6D, which also includes ANSI standard, because that encompasses a lot of different requirements. But exterior source noise control is primarily architect with the design of the exterior envelope. This is where an acoustician can be really, really helpful in either doing the noise measurements on site or helping out with the OITC ratings of your exterior assembly, because those are a lot less commonly used than STC. It's harder to find catalogs of exterior assemblies OITC ratings. And then obviously contractor will be responsible for making sure that the details are borne out in the construction. Mechanical noise, that noise criteria, primarily mechanical engineer who hopefully will be able to do those calculations. They should have the training needed to do it. Otherwise, we've worked with mechanical engineers who've just hired that out to an acoustic consultant as well, and that's more expedient for them and more cost effective for them. For the STC ratings, primarily architect or whoever's designing those interior partitions. Acoustician can be helpful there as well, especially if you have existing assemblies that you want to know the STC ratings of that maybe you're not sure about, maybe they're historical or something like that. Similar case with IIC. And then I'm just going to skip down to the reverb time, the room acoustics. So the architect impacts the volume of the room typically. The interior designer will be the one choosing the materials that will have different noise reduction coefficients. So those are the two primary there. And architects and interior designers should be capable of doing the calculations. There are lots of calculators available that I'll show you one example of. But again, an acoustician can also do that a lot faster than it might take us to learn how to do it. And then making sure that your electrical or AV low voltage is on top of the audio induction loop if that's required in your gathering spaces, and sound masking if that's needed. So during pre-design, you'll want to determine which guidelines are applicable by asking which spaces are regularly occupied, are there learning, are there gathering spaces, sleeping areas, shared walls between different occupancy groups. So this is a program document for our first B3 version 3.1 project that I just pulled together on Friday, listing out my initial impression of which are regularly occupied, which are core learning, ancillary learning, gathering spaces, what the occupancy group is, and then based on those, what the STC between occupancy requirement would be, what the STC within occupancy would be, IIC requirement. You can see that a couple of these, the first two, for example, since they're learning spaces, have different levels for the maximum exterior noise than the non-learning type spaces. I said you can see, but maybe you can't see from way in the back. And then reverb time, would an audio induction loop be required? So I think this programming exercise, especially at pre-design, it will help you understand, okay, how many rated walls STC-wise will I need in this project, and is that something that I should be adding into, having the owner add into the total budget? You'll also want to select which pathway to use for exterior noise, since the one pathway does require that on-site measurement, or just saying you have a high-risk exterior noise site. You'll also want to make sure everybody knows who's doing what. And so this is where in the past we've just had, it's the B3 guidelines tracking tool in the background there. You just have acoustics leader assigned for everything and you have no acoustics leader, so these guidelines never get done. So for this project, it's an old version of the guidelines, but we have the architectural leader assigned to do the OITC and the STC and the reverb time actually in this case. And we have a mechanical leader who is assigned to do the NC requirements, but just making sure that everybody has that in their scope of work, in their schedule, it will really help avoid that problem. When we're doing space layouts, consider where are the loud spaces, where are the quiet spaces, and maybe don't put the disco right next to the lecture hall. Think about room volumes and where you do have walls or where you might want walls. Envelope design, you'll need to do that OITC ratings for your wall and roof assemblies, and then think about any potential synergies or conflicts with energy efficiency, moisture control, daylighting requirements, which are all parts of the B3 guidelines as well. Interior design, primarily looking at the noise reduction coefficients of interior materials. Ceiling height and design also matters quite a bit when we're looking at reverberation time. And then those STCs and IICs of the different assemblies. What about mechanical design?
Well, obviously, locate your sound producing equipment somewhere far away from places. And sometimes more efficient equipment is quieter, which is good. And make sure that you understand that if, say, a listing for a VEV box is for above the ceiling, and there's not gonna be a ceiling, that you understand what impact that has to the rating. There is some guidance that hardly anyone does anymore related to how you isolate equipment, whether it's on a roof or inside a space, what they call a suspended floor or a basement floor. And we don't see that done. I would say I did a survey of Rochester Public Schools. 90% of the base-mounted pumps were not grouted the way they're supposed to, which would all control how much sound is being transmitted by those pumps, because the contractors just never did it. So there is stuff like that that you should understand and know when you're looking at things too, when you're doing it. And obviously, when you're creating the construction documents, list your maximum sound levels for your equipment. You don't have to pick the quietest thing, but you could pick something that is nearly the quietest thing and understand it. Sometimes equipment is available with sound kits to help silence it. There's a big difference in the dampening effect of duct-wrapped insulation depending on how dense it is. You can use the cheap stuff where it's not important and use the better stuff where you want to. And if you feel like you're on the edge and may need to add sound attenuators after the fact, or it's a design build job, you can make sure you have space for putting those in after the fact. So that's, I guess, enough of what you put in construction documents for that.
From the non-mechanical side, you'd also want to make sure that your STC, IIC, OITC ratings are clear in your documents. Your construction details are included to the extent needed for the contractor to comply with them. In the specs, you'd want to list those minimum noise reduction coefficient values for your interior materials if you're counting on those to get you into compliance with that guideline. And then some of these other acoustic testing, audio induction loops, and sound masking, if those are pathways are required for the space that you're doing. In construction, just making sure that things aren't being substituted out that are noisier equipment or less sound absorbing ceiling material, and then confirming that the construction practices are in fact maintaining those ratings that you designed to. In terms of documentation, during pre-design, the only thing that's required is identifying whether or not the project is in a high-risk outdoor noise environment. So that's looking at the airport map and doing that test if you need to. During design and final design, you'll be providing kind of wall by wall or space by space the OITC ratings, STC ratings, reverb time, and noise criteria. And for reverb time and noise criteria, B3 is not actually requiring those to be done for every single regularly occupied space if you do have representative spaces. So if you have 5 classrooms that all are about the same volume, say within 20%, have the same floor material, ceiling material, same general wall materials, doing the reverb time calculation for one of those and saying it's representative is accepted. And then similar with noise criteria, which may be more about proximity to the noise source than necessarily about similarity of the different room types. And then also providing, if required, a design description of that audio induction loop. In the closeout phase in the tracking tool, you aren't required to do actual on-site measurements. So this doesn't mean that you're having the STC ratings confirmed. It just means that what was included in the construction documents actually did get built or the equivalent. So it's just signing off and saying it didn't change to have a huge hole in the wall or to have a different, we have no ceiling now because of value engineering. You know, big changes like that is what that's intended to account for. So we have 10 minutes left. Are there any questions before we go into really quick demos? Yes.
Are there concrete block walls and solid concrete walls listed in the ANSI standard 12.60?
The wall types aren't listed specifically. That would be more in the, like the sound transmission
Yeah.
class. So that would be listed in sound transmission class guidance, and there are some of those in
In
this
the
HUD
others.
version. Yep. They might or might not be in, the gypsum board versions of them, but they should be available otherwise. Okay, David is going to have 2 minutes for noise
Oh,
control.
yeah, okay, 2 minutes. Okay, well, I was thinking it would have been wonderful to do a live version of it, but it got too complicated. So, basically when we're doing this, we, doing a noise criteria calculation for a room. We're gonna start out with the equipment that's making the noise, which is your rooftop or an air handling unit. This happens to be an air handling unit shop drawing from a job of ours. And you can see that we have octave band information. It's only from 62 up to 8,000. And then we have the power. We talked about sound power, which is LWA, and we have DBA. And then we have each octave band by the inlet condition and the outlet condition, because sometimes it makes a difference which way we're going with the airflow. The B3 guidelines point you towards this particular document, which is a AHRI, which is the air conditioning refrigeration industry. It's a freebie. It's a spreadsheet that was done in 1995, so it's 20 years old. It calls for things like interior insulated ductwork, which we haven't been able to do in Minnesota since about 1985. But anyway, what you do with this is you plug in your duct size, on the left-hand side, your duct size, if you had lining in it, how many elbows you have, how many T's, what does it take to get to the first room that's gonna be affected by it. And then basically in the middle there, it's telling us, well, this is how much reduction you're getting for each of those items. And then the bottom is telling us how much sound is getting to the space, up to the edge of the space. And then we go to the next one here, which has us looking at the room attenuation itself. So the sound has gotten to the room on our first spreadsheet tab. Our second spreadsheet tab, we're looking at the room criteria and seeing what the room is doing to it, how much attenuation we're getting there. And then the next spreadsheet has got how much sound is coming from the diffuser and the VAV box, and these are getting added in. So this was the question about the NC20. They actually don't want you to plug in the NC20, they want you to do it by octave bands. So for instance, one of the major manufacturers based in Texas, you can use their software package called Teams, and it will give you that information. Instead of just a NC20 number, it'll give you the octave band information, and then you can plug that in. So it's some stuff we haven't necessarily done in the past to use this software, but it does give you the room sound in NC plot, and you can figure out what you have here. So that's the way that works. The other thing you can do is some of the manufacturers offer this for free. This one you pay for, it comes from a manufacturer down in La Crosse, and you basically have these little blocks and you can kind of put things together, connecting them with lines, and you can say, okay, in this case I did a chiller because it was easier for me than an air handler, but basically you put a wall in, you put the room conditions in, you say where you are, and in the end it gives you the answer down below. It says it's a NC 16 inside this particular room. But that's the contribution from a chiller, so that's a little different than normal. Anyway, that's a very quick NC demo. A couple ways to do it. Use the spreadsheet, which will be more difficult, or hopefully you have, if you're a mechanical person, you have a software, you can just plug it in. Daikin has it, Trane has it, I think Carrier has a package you can use that are not terrible to use. Again, you don't have to do every room anyway. So for the most part, on air handling equipment, you're gonna pick the closest kind of representative rooms to the air handling equipment, because the sound is dissipating by the cube of the distance, so.
Thank you. Okay, and then finally, we have a quick reverb time demo. So just a reminder that the reverberation time requirements are somewhere between 0.2 and 0.8 seconds, depending on if you're a learning space, core, ancillary, open office, or other type of regularly occupied space. And again, this is required in the 500, 1000, and 2000 hertz octave bands. So in general, the reverberation time is dependent on the volume of the space and then the effective sound absorbing area. And then there's a constant over here that's in seconds per foot. So you get seconds out of it. So basically, all this is to say that a large volume with reflective materials or non-sound absorptive materials is going to give you a high reverberation time, and a small space with a lot of surface area that's absorptive, like that image, will give you a shorter reverberation time. So you can do it manually by looking at the absorption coefficients times each of the surface areas with the volume up here and that down below at each of the frequencies that's required. Or if you don't want to do that, you don't have to. There's plenty of calculators available. So this is just one example. Happens to be from Armstrong. So we pick, the things that are important to type in are the dimensions of the room. So let's say a classroom that might be 30 by 30 with 9-foot ceilings and 4 walls. None of this information matters to the reverb time, so let's see if they'll let me do it. Yep. Okay, and then for each surface, basically, it's asking for what the materials are. So here they've put in a bunch of their own materials, but I can just choose drywall for the 4 walls. I can say if there's a door or window, I can add that in as well. And then what is the floor? So say we have linoleum on concrete. What the ceiling is, again, they have all of their products, but they also have a generic ceiling with NRCs ranging from 0.5 to 1. So I'll put kind of a high performance but not super high at 0.7. And then for this one, we do want to actually make sure we're including, the ceiling typically isn't 100% covered with that type of material. It also does include light fixtures and air grills. Might be anywhere between 5, maybe up to 20%. We'll say 5 there. So then, clicking next, and we see we're looking in this 500, 1000, and 2000 range. They have their recommended reverberation times, but we know that ours need to be under 0.6 for a learning space like this classroom, and it is in fact under 0.6 at each of those ranges. If we went back and said, oh great, can we take out the ceiling and leave it as, anybody see concrete? Concrete. What does that do? Okay, now it's up to 3.58, 3.8, 2.67 seconds. So that ceiling material in that case was pretty much the only sound absorbing material in the space, and it's a large enough room that it's echoing around and has a long reverberation time. So through this, you can play relatively quickly with, okay, what if I raise the ceiling? Well, if I do that, that NRC ceiling of 0.7 is no longer going to be high enough. I'm going to have to go up to 0.75. So you can relatively quickly understand with different dimensions and materials what type of reverb time you'll be looking at.
What does treatment do? Does that just add stuff to the walls?
Yeah, that has different Armstrong specific solutions that you can add in to get it within the requirements that you'd like. So reverberation time resources, that type of calculator are available online, whether manufacturer specific or not. Many manufacturers may also offer customized reverb time calculations if you're using their products. So that's something you could consider taking advantage of, and advice on acoustic solutions. So if you don't mind going with a certain line, you can do that. Again, an acoustic consultant would be able to do these as well, especially if you have more complicated geometries or spaces. And then they can offer third-party advice on acoustic solutions. We have a slide in your packet about cost implications. Some of these things will cost more, both in a little bit more in the design phase and potentially more in the construction phase as well for those rated systems, more efficient equipment, and other things. So with that, we'd like to thank you.